Welcome to Sundar's lecture. This is lecture number 25, and in this lecture we are going to see dynamic hazards and then programmable logic arrays and then programmable array logic. So we will see that one later. So what are the topics we have seen in the previous class? See, we have started with the hazards, right? Glitches and then hazards, and we have seen what is static 1 hazard and with some examples. So and then we have gone to static 0 hazard. We have taken examples to understand the static 0 hazard in the previous class, and also how to detect the static 0 hazard, how to cover the static 0 hazard. We have taken some examples and we have seen in the previous class, and in this class we are going to see dynamic hazards. So what is dynamic hazards? Potential for multiple transition before settling to final value, while Boolean asks for only one transition, which means, for example, if you change any input, the output is expected to change to a different value. For example, if any one input is changing, maybe the output has to change from 0 to 1 or 1 to 0. Instead, what the output will do, it will do like this. For example, if the output is expected to change from 0 to 1, it goes to 1 and then comes to 0 and then goes to 1 again. So you have multiple transition in the output, which means 0 to 1 and then 0 and then again 1, or it will come, the output has to move from 1 to 0. Instead, what it will do, it comes to 0 and then 1 and then again 0. So there will be multiple transition, and these are called as dynamic hazards. And that is what I have written here. One input variable has 3 or more paths to the output. So when it will happen, if there are 3 or more paths for a single input to reach the output, then this dynamic hazards will be taken place. And number of levels, it will be 3 or more. We can also understand by the equation. For example, we have seen when static 1 hazard will come, it will be a tautology, that means a plus a bar, and when static 0 hazard will come, it will come when the equation has fallacy, that is a dot a bar. Like that, you can also conclude when a dynamic hazard will going to happen in the circuit. There are two conditions. One is either a plus a bar dot a. The expression has to be like this. For example, a single variable, we are going to change a single input, and that input is this one. It may be a, b, c. The representation may vary, but if the expression becomes like this or like this, we can conclude that maybe you can make like this also, like this, then we can conclude there will be a dynamic hazard, right? So what we will do, we will take an example. See, this is the circuit, this is the output expression, and you see this is the output expression, which means what we are going to do, we are going to substitute a is equal to 1, b is equal to 1 and d is equal to 1, and then what happens in this expression now? What is the expression? A is 1, so that it will be c plus, and b is 1, so it will be c bar dot. Here you see c is there and d is 1, so you will get like this now, the whole bar, right? So here comes the problem. You are getting an expression like this. So here there will be a dynamic hazard. So let me explain that one. So what we are going to do with this one, that means we are going to keep a is equal to 1, b is equal to 1, d is equal to 1. We are not going to change anything, but we are going to make c, maybe c which is equal to, we are going to make this 1 to 0, making c is equal to 1 to 0. Then what happens in the circuit? See, first, before condition, I just want to write it down. So this is 1, and already c is 1. So I am just writing this one in the blue color, right? So already c is 1, and this b is 1. This is 0 because c bar is 0, because c is 1. I am just considering the c is 1. So I am writing the previous condition. So this one is 1, and this one is also 1. So what is the output here? So this is 1, this is 0 and this is 1. So this will be 1 and this will be 1. The output will be 1. So the output will be, oh sorry, this one, since it is 1 1, so if you put 1 1, so this will become 0, right? So 1.1 will be 1, so 1 bar will be 0 and this will be 0, so output is 0, right? If you give A is equal to 1, B is equal to 1, D is equal to 1 and then C is equal to 1. And what I am now going to do, I am going to change the 0, 1 to 0. So what happens here, I will change this to 0, this to 0. So maybe I will take a different color. So this to 0 now. So if I make this to 0 and here it is 0, here it is 1, right? So I will take this y1 first, this y1. So what happens here, this y1 is going to become now, it should become 1, right? Because if I give 0 1, 0 1, the 0.1 it will be 0 and bar will makes this to 1. This gate will take a propagation delay, 1 delay, maybe you take it as 1 delay and then it is going to 1. So that is what I have done here. So in this instant I have made C to 0, but it will take 1 propagation delay, so and then only it is going to 1. Already it is 0, it is going to 1 after 1 propagation delay. That is what I have just written here, right? Y1, that's all, completed. Now you go to Y2. What happens here? This is 1 already and now we are keeping this one to 1, but this 1 is going to 0 here. This is 0. And what happens now to Y? Already it is in a high, it is in the high, that means output is 1. Now I am making it to 0 so that this 1 will goes to 0 after 1 propagation delay, because this gate will take a 1 propagation delay. So that is here. So it is already 1. That one propagation, after 1 propagation delay, it going to 0. That's all. So we have completed y1 and then y2. Now go to y3 now. Y3, what happens now? This is 1 already. Now I have changed this to this C2. Already it is 1, right? I am just changing this to 0 so that this gate is taking 1 propagation delay to make this to 1. And if this is 1 1, now it is going to be 1 after here 1 propagation delay. This will take 2 propagation delays. Since this take 1 propagation delay and this gate again take another propagation delay, then only this will makes to 1 from 0 after 2 propagation delay for y3. See here, 1 propagation delay, 2 propagation delay, and then only it is going to become 1. Simply. Can you understand what I am saying, right? So now you check what will be the output for y4 and then y1, right? For y4 it is a 1 gate. So what y4 will do now, this is going to 0. For y4 what you do, you just check for y2 and then y3. When y2 and y3 any one is 1, then it will goes to 1, right? Check it out, this for at this instant y2 is 1 here, y2 is 1 and y3 is 0. So what happens now, this y4 will stay in 1, no problem after this point, right? And it will stay in 1 here, and at this point you see, at this point this y1 is going to 1. Sorry, I don't see y1, I need to see y2. See, this y2 is going to 0 and this y4 is 1. Sorry, this y3 is 0. So you see what is happening over here. At this instant y2 is also 0, y3 is also 0, right? This one and this one. So if this gate will take 1 propagation delay to change this output to 0 now. Since both are 0, so what happens now? Taking 1 propagation delay and then it is going to become 0. Simply, right? So can you understand? Now this has came now. Now it will check for the second instant. Now you see this y2 is 0 here, but what happens to y3 here? It is 1 now. So what happens after one propagation delay? This is the propagation delay. This will goes to 1 again. Can you understand? Can you understand? This has goes to 1 now. So y4 has goes to 1 after one propagation delay. This is this propagation delay and this has become now 1. So this is y4. We have completed the y4. And now you come to y. So for y, what you need to do? You have to check for y4 and then y1. Right? If any one becomes 0, the output y will goes to 0. Right? Can you understand? Right? This is how this is what we are going to see it now. So what we have to see y1 and then you see this y4. What happens at this instant? This is 0 and y4 is 1. So if it is 0, then after one propagation delay, the y will be 0. Since this is 0 and so y will be 0, no problem. And you see at this instant, see here what happens. This y1 is 1. This y4 is also 1. Try to understand. Both are 1. Here also 1, here also 1. So after one propagation delay, this output y goes to 1 at this point. Right? Now, it will check for the second one. This is 1. This is 1 at this instant. That means y1 is 1. But what happens to y4? It becomes 0. It becomes 0. Right? So the output has to come to 0 for the next. It take one propagation delay because of this gate, and it comes to 0 here. See here. Right? This has become 0 at this point, and it has to check for this condition. This y1 is 1 here, and you see this y4. This y4, it is 1 here. So both are 1 here. Both are 1 here. So after one propagation delay, it will be 0 for this one. After one propagation delay, this will goes to 1 again. And afterwards, no change. No change. So these both will be high. So always it goes to 1. Try to understand. Try to understand. So what happens now if this one goes to this one goes to 0? This one goes to 0. Maybe I will put this is equal to 0. So if you substitute in this equation, you will get y to be 1. Take this condition 1, 1, 1, 1, 1, 0, 1. That means a is equal to 1, b is equal to 1, c is equal to 0, d is equal to 1. The output has to become 1. So what is the problem here? If I change this c from 1 to 0, the output has to become 1 from 0. So this output has to go to 1 after changing the 0 to 1. But instead what is happening around here, the output is 0, it is going to 1 and then coming to 0 and then it is again going to 1 and it will stay at 1 for a long time as there is no change in y4 and then y1. So what is the expected output? It has to become 1, then I change the c from 1 to 0. But instead it is just oscillating between 0 and 1 2 to 3 times and then it is coming to the expected output. And this is what we are calling it as dynamic hazard. Can you understand what is dynamic hazard now? Right? So this is called as dynamic hazard. So how will you eliminate this dynamic hazard? Try to eliminate the static 1 hazard and static 0 hazard. While using the Karnaugh map, you just eliminate the static 1 hazard and 0 hazard, automatically dynamic hazards will be eliminated, right? So that's all for dynamic hazards. So we will move on to the next topic. So the next topic is programmable read-only memory. See, I am not going to teach you what is PROM, what is PAL, what exactly inside the PROM and those kind of things. It is a structural part, so I am not going to cover all those parts. I am just going to explain you how to implement a Boolean expression in PROM or PAL or PLA. That's all. That is my ultimate aim. So I am not going to explain you the structural part. So you just, if you want to learn the structural part, go to some other videos or some other content. If time permits, I will just also cover the structural parts of PROM, PAL and then PLA. Right? So I am not going to cover that one. But what it actually means. PROM allows the user instead of manufacturer to store data. What we will do, we will take a PROM chip. In that, what is the expected output that can be programmed by the user. The manufacturer will manufacture and fuse all the possible things, and we can blow out the fuse to get the desired output as we expected. So an instrument called PROM, that is programmer, stores the work by burning in. By burning in, which means we are going to remove the fuses that is connected in by means of the diodes here. So originally all the diodes with the fusible rings remains connected across points, and then the PROM programmer sends the destructively high current through the diodes that are disconnected. So what is the thing here? You see, this is the input now. This is the 3 input system. So how many combinations will be there? Then obviously you will have 8 different combinations, right? So it will be A, B bar, C bar, and then 0, 0, 0, 0, 0, 1 until 1, 1, 1. So all these are fixed ones. Try to understand. You cannot program this one. This is a fixed R and array. But what we will do now, this is the output now. We will have multiple outputs, Y0, Y1, Y2, Y3. And in every outputs, there will be the expression, SOP expressions will be there, like A bar, B bar, C plus A, B, C plus A bar, B bar, C bar, and that's all. If it is so, then this is a programmable R array. This all are connected. For example, if Y0 is only ABC and then A bar, BC, then what we need to do? We need to blow out all other these 2 fuses. This is fixed. With only these 2 fuses has to be kept. For example, maybe I will write it down. If Y0 is equal to ABC plus A bar, A, B, C bar. For example, we will take this one. So these 2 has to be fixed. And what happens to these all other fuses? We need to blow out this one, blow out this one. You have to blow out, blow out, blow out, blow out. You have to blow out these fuses by sending the high current through the diodes. These are all connected by a diode. So these 2 are fixed, which means we are keeping these 2. All others has to be blown out. Try to understand. And for example, if you take Y1, you can blow out anyone. So what is the thing you have to understand? This is fixed. You cannot change this one, but you can blow out these fuses. That is programmable read-only memory PROM. Right? So can you understand what is this one? So what we will do now? We will go to PAL and then PLA. Everything comes under or related to PROM. So in PROM, AND array is fixed and R array is fusible. That is what I have written here. Fixed AND array, R array is the fusible. And the next one, it is programmable array logic. In that, R array is a fixed one. See here. See here, R array is a fixed one and AND array is a fusible. You can change this one. Try to understand, right? And we will have another type, that is programmable logic array, PLA. In this one, both AND array and then R array can be fusible. You can do both things. Try to understand. That is the difference between PROM, PAL and then PLA. Try to understand, right? So what we will do now? We will see this one. This is PAL. And what is PAL? We have seen here. See this one, fusible AND array, but R array is fixed here. So you cannot change this R array. Try to understand. There are only 3 outputs comes away from this one. So this is fixed. This is fixed. This is all fixed here. Try to understand. You cannot change this fixed one. But what you can do instead, this one is the AND array. You can blow out the fuses here. You can blow out the fuses. So what we will do, maybe you can take this output and you can give it down to here. Maybe you can take this as now D0 and then D1 bar. If the outputs has repeated multiplication terms, then you can reuse that. You can reuse that by using the AND array fusible, right? So anyhow, maybe we will take an example so that it will be easy, right? So we will go to this one. So implement the following Boolean expression in PAL. So this is the expression. So we have 4 number of expressions and we need to simplify this one using the Karnaugh map. And if you simplify, so I will write down the simplified equation here. So see here, after simplification you will get this one. I have done the simplification using the Karnaugh map and I am getting the reduced expressions like this, right? So how will you implement this one in PAL? That is the idea. So I will just copy down this one and then I will explain you. Right. Now you see this is the PAL structure and these fuses, all the fuses will be in contact. Right. Try to understand like this. Like this, all the fuses will be in contact and now you see this is W, this is X, this is Y, this is Z. That is what I have done here. But what you need for W, it is A, B, C bar. So this is A. See here, this is A and then B, C, C, D and I have connected all these things. And what I have done, I have just taken the W also with as an input because you can compare this W and this is Z. You can see this is actually W. We can write like W plus A C bar D bar plus A bar B bar C bar D. You can write like this one. So what you can do, you can also use the any of the multiple output terms. We can use it in the other one. Right? So that is the idea. So you see here, it is A B C bar. So it is A B then C bar. That is those 3 fuses will not be blown out. All other fuses in this AND gate has to be blown out. And you take this one now. This is A bar, B bar, C, D bar. And this is that one. So A bar, B bar, C and then D bar. All other fuses will be blown out. See, you have 16 combinations are there. I have not shown you here. Anyhow, we can get whatever the number of AND gates you are required as per your output expressions. But all these are fixed, right? So this is the idea, right? So what I have done here, and you see this AND gate is not used because we don't need to see this one. What you have to understand here, if you take any PLA structure, it will come by a product like 3 AND gates and then 1 OR gate, 3 AND gates, 1 OR gate, 3 AND gates and 1 OR gate. Like this, you will have 4 number of output combinations can be implemented with 3 and possible 3 equation possibilities. Try to understand, right? So this is how you can implement, right? There are so many ICs are there. Using those ICs, you can get whatever you need as per the requirement. Maybe this one I have done this one, so this is not required. For this output only 2 are there, so I can leave this one, as well as for this X, see here only 2, so A is connected through this one and then BCD is connected through this one, and this is not required because I need only 2, and for this one I need 3 because I have 3 terms, so all the 3 terms has been used here for Y, and for EZ I have 4 terms here, but but my package is not having 4 AND gates, but instead what I am having here, I have just taken this output and I have just used this output as a one input to the other output. That is what I have done here. So what I am doing here, these R arrays are fixed, but these AND arrays are programmable. That is what I have done. We have programmed this AND array to implement this Boolean expression. So this is with PAL, right? So what we will do now, we will take an example to understand PLA, because I am not showing you the structure for PLA. Since there are numerous structures are available, you can either connect AND gate array, or you can connect the OR gate arrays. Both are programmable. So I will directly take the example problem to explain you things how it is working, right? So this is the expression for a given question to implement the Boolean expression in PLA. They have given only 2. Only 2 expressions has been given. So what I will do now, I will just simplify this equation and I will write it down here. Simplified expression using Karnaugh map. So you see here, I have just simplified this F1 and I have written the minimized Boolean expression. But what happens with the F2 now? So I'm going to do a simple logic thing here so that it will help us to implement that in the PLA, right? So what is that one? See here, this is the actual K-map for F2. So if I simplify this F2, what I will get as an output here, let me find it out. So F2 will be is equal to, for this one, it will be B bar and then C bar, put plus, and then for this one, this is a pair. So anyhow, you see there is a quad possibility is here. So we can make this as a quad. So if I am writing F2 which is equal to what is this term. So if you go for this term, then what is the common term in these two? It is C bar. So C bar will come, put plus, and if you take this as a pair, so it will be A bar, and in these two it is B bar. So what is the problem here? You check this term A bar, A B bar, and then AC plus A bar B C bar. So you have 5 different terms, 1, 2, 3, and then 4, and then 5. So you need to use a 5 different AND gates here. So I will explain you. Maybe if I put the graph, if I put the PLA, then it will be very simple. But instead, what I am doing now, I will take this as 1 and all these to be 0, so that I can make this to be F2 bar. I can make like this, right? So if I write F2 bar, now you see this is a pair, this is a pair, and if I write this one, this is a common term, that is A here, and what is the common term of these two? 1 is the common term, so it will be C. Put plus, and then for this one it will be BC. And try to understand one thing here, this AC is here as well as here. Now how many common terms are there in both F1 and then F2? 1, 2, 3, only 4. So that we can eliminate one AND gate term here. So that it will be very easy to implement it in the PLA. So that is why what I am going to do, I am going to take this as to F2 bar now. Right? So what I can write now, this F2 can be written as AC plus BC the whole bar. Right? Just put bar here, so that put bar, maybe you will get this expression like this. And what I am going to do now, I am going to use only 4 different AND gates, because I have 1, this is 2, this is 3, and this is 4, right? So for these 4, I have just used here, see here, A B bar, and then AC, and then A bar, B C bar, and then BC. Only 4. Right, so what I have done here, I have just mapped this one. So this one is also programmable. So what I can get now, a package of 4 AND gates and only 2, maybe 2 OR gates. Try to understand. Not 5 AND gate with 2 OR gate. If I use this one, use this as my output expression, then I have to buy a 5 AND gate array and then 2 OR gate. 2 OR gate is very simple to understand, since it is F1 and F2, there are 2 outputs, so you have to go for 2 OR gates. So what I have done now, I have just implemented this one with the 4 AND gates. I have reduced 1 AND gate now. So what I have done, so I have just taken this one and I have just make this output lines, and then for F1, I need to connect this one A B bar and then AC. See here, for the first output, see here AC. Maybe if I missed anyone. So for F1, I have mapped this one. Okay, fine. Three are there. So A B bar has been mapped here, and then for AC I have mapped here, and then for A bar B C bar I have mapped here. So now this will be output comes here. Maybe I will explain you. You take this as now the output here, and then I have used these two, for these two, AC and then BC bar. So this is AC, and then this is not BC bar, it is BC. So this is comes out now. So actually, what is the output will come in this one? It will be direct output, that is AB bar plus AC plus A bar B C bar. I don't need any inversion here, right? I can put directly to the output now. So what I am doing now, I have taken an XOR gate here. What XOR gate will do if I give one input to 0? It will act as a buffer, right? So it will pass through the output. I have already told you, please refer to my previous classes. I have explained you what happens if XOR, one input of the XOR is by default 0. It will pass through. So this will be passed through to output. This is now F1. So straight away I will get this one now. Straight away I will get this one. But what happens now for F2? For F2, I will get an expression like AC plus BC here. Those two expressions only I will get here. But what I have to do, I have to make that as a bar. So for that, what I will do, I will take an XOR gate here. That XOR gate, if I give one default to one input, that is what I have done here. See here, I have given this one to one input of the XOR. So whatever I am getting here, that will be converted as X bar. We know this one. So this one I am getting here. So what happens to this one now? So this will be now AC plus BC the whole bar. Try to understand. So the idea is getting the package is the difficult thing here. So I am getting 4 AND gate and 2 OR gate package as a PLA. If I am not done this one, I have to get 5 AND gate and 2 OR gate package. And that is what this one. So you can implement as many as problems. It is very simple now. So just simplify and get the output expression, and those output expression count how many number of AND gates you need, and depends on output expression how many number of OR gates you need, you can conclude. And with that you can just draw this diagram and you can put it down simply. But this one PAL, you can get this many number of AND gates with how many OR gates are connected. This is fixed here. You cannot change this one. So this is PAL, right? So what are all the topics we have seen in this class? That's all we have concluded now, and I will start a new topic in the next class. So what are all the topics we have seen in this class? So we have started with the dynamic hazard. What is dynamic hazard? Dynamic hazard, when the output is expected to change from 0 to 1 or 1 to 0, instead it will goes to multiple transition and then settle down to the expected output. That is called dynamic hazard, right? And when it will happen, when these expression exist, right? I have taken an example and I have explained you what is dynamic hazard, and then we have gone to programmable read-only memory PROM. What is PROM? In PROM, and R array will be there. Both the AND array is fixed here, and then R array can be fusible. And we have seen what is the difference between PAL and PLA. Here it is AND array is fusible, R array is fixed, and then in PLA both are fusible, right? So we have taken an example to implement the Boolean expression in PAL, and we have taken another example to implement that in the PLA, right? So we will see in the next class. Thank you.